Hi students, welcome to our last class of our Metallocene and Metal-carbene based organometallic catalyst for industrially important polyolefin catalysts. Today we will discuss some of the industrially important polymers which are synthesized by ring opening metathesis polymerization by different metal-carbene catalysts. And so far what we have discussed very elaborately about the different type of ring opening, different type of alkene metathesis reactions. Then we have discussed what is ring opening metathesis polymerization, what are the catalysts involved, and we very deeply we have discussed that what are the metal carbene complexes, what are the category of the complexes, what the electronic properties, what is the designing of the different ROMP catalysts, and we have extensively discussed the mechanism of ROMP polymers. Today we will discuss mostly some of the industrially important polymers which are actually achieved by ring opening metathesis polymerization reactions. So let's start. So today we will cover the concept of industrially important polymers by ROMP, and another very interesting and industrially viable process is the ROMP in aqueous phase. Why it is important? Because you know that organometallic catalysts are generally not water, not air stable or moisture stable. So it actually limits our uses in ambient conditions, and which are basically kind of a negative if you want to sell it as a industrial method. So we have to, for a practical implications, my catalyst should be stable at ambient condition, and if the reactions or polymerization reactions if we can do in the universal solvent like water, then our process will be much cheaper and it will be more greener. So the recent development and how we can convert or how we can design the catalysts for aqueous phase polymerizations, that we will discuss. Very interesting and very just a little bit tuning of the catalysts we will discuss. Okay, so you know that we have so far discussed what are the advantage of the ring opening metathesis polymerizations. We have realized that ROMP is one of the very versatile method in polymerizations. There are a lot of advantages, okay, which are, and that's why it is becoming very popular, not even in the academic, okay, in the lab, but also in the industries. Okay, so many industrial processes are based on the ring opening metathesis polymerization by different type of catalysts. So there are some points I have here pointed out, like usually as we have already discussed that this polymers is living in nature, so you can get a high molecular weight polymers, okay, and not only that, you can also tune the architecture, because as it is living, you can make the different type of architecture polymers like block copolymers or other type of functional polymers. These are also you will see that these ROMP by the metal carbene catalysts are compatible with other functional groups attached in the monomer. Another, you will see relatively unstrained, okay, monomers can undergo ring opening metathesis polymerization. You will see that metal carbene reactivity is more important than the ring strain, because if the ring strain is the prime factor, then norbornene or octene, which have a very less ring strain, should not undergo the ROMP. But we have seen, obviously, yes, the monomer cyclic alkene cyclic olefin monomer which has more ring strain, that obviously will go polymerize easily, but it is also shown that the monomer with less ring strain can also undergo the polymerization. So metal carbene reactivity is one of the prime factor here, and that's why you different type of catalysts have been developed time to time, like first generation graph to second generation, like that. And you will see that many simple or cheap catalysts have also been developed, because you see, if you want to make a process industrially viable, then the catalyst will be cheap, synthetically should be easy, and also the handling of the catalyst should be very easy. Otherwise, it will not be industrially viable process. So time to time, you will see that is one of the example, which you will see that ruthenium chloride can also do the polymerization easily to get this kind of a ROMP polymers. Okay, and most importantly, to make it a industrially viable, the catalyst must be reused, recycled, and here, yes, this also qualifies this criteria. So it's basically, you will see, this is one of the most of the criteria to be industrially viable is qualified by the this kind of metal-carbene catalysts. Okay. So these are the today, as I told, that I will highlight, although we have discussed in previous classes in discrete way the monomers like this. Okay, I want to highlight how and why these are industrially important, and these actually produced this particularly these three polymers are produced commercially and by different polymers industries. First one is, you see, the polynorbornene, we all know. Okay, this one is the polydicyclopentadiene, and this is the polyoctanomer. Okay, we will discuss in more depth. Okay, you will see that very interesting, and why these polymers are so important. First two polymers, why these are so industrially viable, because you will see that the monomer, okay, for the two monomer, this one and this one, you will see these two monomers are actually linked with the cyclopentadiene. So this is actually cyclopentadiene. Okay, and how do we get it? Any idea? Okay, we actually get it as a byproduct, okay, during naphtha cracking or petroleum isolation industry. So that means it is actually byproduct. So if this can be used for to have a other valuable products, like here you will see that commercially important polymers, then the whole process will be much cheaper. However, the cyclopentadiene you cannot really buy commercially, because it undergoes a desolder reactions. Okay, this is, you know, that in you have a desolder reaction, so it undergoes a cyclization and make a dimer. So this is a monomeric form. Okay, and this is actually dimeric form. However, you can convert to dimeric to monomeric very easily just by heating 150 degrees centigrade temperature. You will get the, so it's basically that happens the retro desolder reactions. Okay, so in this is commercially available. That means why it is commercially available, because although we get the cyclopentadiene by the cracking of the naphtha process, it actually spontaneously diverges into dicyclopentadiene, and this is actually the isomer. You know that it is a two isomer, one is the endo, one is the exo. Okay, so this is actually the endo. Okay, dicyclopentadiene. Okay, so you will see that this one is the monomer for the polydicyclopentadiene. This is also called the PDCPD. Okay, polydicyclopentadiene, and here you will see that this cyclopentadiene, if you react with ethylene, it undergoes the reactions and forms the norbornene. So this is actually norbornene. Okay, so you see that from a single substrate I am getting the two different monomers, and the main precursor is actually obtained from as a byproduct of naphtha process. And another one, you will see that this is also commercially important, that is the polyoctanomer, and here what is your monomer? This is actually cyclooctene. Okay. So, let us discuss in little more depth about these commercially available polymers, commercially important polymers. These are, as I told, this polynorbornine. This is first marketed by the a France chemical companies called CDF Chemi, okay, back in 1976, and the trade name is Nor-Sorex. So, this is actually named as a the polynorbornine is nothing but the Nor-Sorex. This is the trade name, okay, and you will see that there are a lot of different applications, even though it is very important and valuable. Most of the one of the interesting and important application is used in the oil spill recovery, and also it is used as a soundproof materials. Okay, very good soundproof properties it has, and this is one of the heavily produced polymers by ring opening metathesis polymerations. So, this is one of the another polyoctanomer. So, the trade name is the Vestenamer, and this is actually marketed by first synthesis structured by KMC Werkhulz in Germany and marketed by Hulz AG since 1980. Okay. The catalyst is basically molybdenum based catalysts, and you will see that there are different type of polyoctanomers are produced. There are some typical trade names like Vestenamer 8012, Vestenamer 86213. So, here the first 2 digit actually you see it's actually tells the double bond character, how much percentage of double bond character. So, here it is like 80%, and this one you will see 62% like that. Okay, the average double bond percentage, and the last 2 number is the viscosity number. So, this is the viscosity number you will see. Okay. So, this is the kind of a convention to identify the different type of Vestenamer polymers. Okay, and is used as a rubber processing aids and different type of so like we have previously discussed that the applications of polyisoprene, polybutadiene, those kind of. Okay. So, a similar category of the polymers, okay, the polyoctanomer. Okay. And most important and the recent addition of the ROMP polymers is basically PDCPD, that is the poly dicyclopentadiene polymer. So, you will see that this is the dicyclopentadiene monomer, okay, and this is my polydicyclopentadiene PDCPD. The trade name is as Meton, okay, and this is marketed by the US companies Hercules, and you will see that, and this is very interesting in nature, because you will see that this one is polymerases, but you have another alkene bond. Okay, this alkene bond you can further take a advantage of this alkene bond, and you can make a different type of polymers functionalize, or you can take the advantage of the alkene for fine tuning of the property, fine tuning of the synthesized Meton polymer, that is the one type of PDCPD. Okay. Now, this is you can consider as the first step. Okay. And the second step, if you have catalyst is quite active, then it can also do the second step, and here you will see that it is actually you will do the polymerations here. So, you will make a highly network, okay, highly cross linked or network, okay, network polymer. Okay. The trade name of this one is Telin. So, first one is the Meton, this one, and this one is the Telin. And the properties, as you see that these are, the tellene is nothing but the cross-linked version of the metal, that is the PDCPD. So, obviously the properties will be different. The most important property of the this kind of PDCPD is the stiffness and the toughness. Okay. So, here you will see that this is the metal and this is the tellene. Tellene is the cross-linked. You will see the tensile strength is quite different. For this one is 6200 psi, this is 6500. Okay. And glass transition temperature, you will see that this is 138, this is 155. These polymers are heavily used in different segments like automobiles, mechanical industries, like that. Here you will see body panels for truck, cell cover for different type of industrial plants, different type of equipments, and most importantly that you will see that 1.5 inch of poly DCPD resin is actually can prevent from the bullet. You will see that 9 mm bullet. So, it is so strong in nature. Okay. And even you will see the block copolymers of polynorbornene and decaborane useful in synthesis of nanostructured boron carbonitride. That means the polymer, you will see that how stiff and strong it is. Okay. So, these are polymers are very much used in our daily life. Okay. The PDCPD category, and all are synthesized by the metal carbene based catalysts. Other important polymers, like you will see that the first one very much similar like norbornene. Here you will see that the 1,5-methyl, this is the methyl group. Okay. 1,5-methyl 1,5 cyclooctet diene. Okay. Sorry, this is not okay. 1-methyl 1,5 cyclooctadiene. So, here you will see the ring opening polymerization will give a elastomers having alternate copolymers of isoprene and butadiene. Here you will see this part is isoprene and this part is the butadiene. So, it is a kind of a, you will see that you no need to no need to charge two monomers, that is the isoprene and butadiene. You are taking a single monomer and you are getting a alternating copolymers of isoprene and butadiene. Okay, which is a good elastomeric, having elastomeric properties. Okay, catalysts are again the tungsten based catalysts. And here you will see that 1,357 cyclooctatetraene. Okay, because you have 4 bonds and you are getting a polyacetylene type, polyacetylene polymers. You know that these polymers are semiconducting in nature. Okay. And one of the hot research topic is the developing the semiconducting organic polymers for flexible photovoltaic devices or OLED devices. So, these are, you will see that semiconducting polymers can also be synthesized by ring opening metathesis polymerization. So, these are really, you will see that there is no doubt that these are versatile polymers with versatile properties, and functional groups can be synthesized by the ROMP catalysts. Okay. Not only that one, okay, you will see that there is one very interesting and what is I call that applications or the thought process, how I can make my polymer as smart. Okay. Here you will see that this is the cyclodipentadiene monomer, and synthesized you will see PDCPD. Okay, that is the meton, and then you can use utilize the leftover alkene moiety to make it a kind of a grafted polymers or cross-linked polymers. Okay. Now, with this fantastic properties, we can also make a self-healable smart polymers. What is self-healable? You will see that many times what happens, the polymer surface, okay, like if you have a polymer surface like that one, it may give a crack, okay, like that. Okay. Now, this is dangerous, because if it happens in a very kind of a sophisticated applications, as example, let's if it is like a aircraft, okay, or let's say in a spacecraft, then what will problem? There will be permanent damage. So there will be some mechanism to heal it, self heal it, okay, so that this again it become a normal things, okay. This is called the self healing and become, so this heal will be cured automatically. So with this one you will see, if I incorporate this monomer in my main polymer skeleton, and then if I treat it like this kind of a catalyst, then due to the network structure, then again it will be healed. So that means, suppose this is initially it was my a homogeneous surface, and then due to cracking it crack like this one, okay, and then if I have a self healing properties, then again it will be cured, okay. So this kind of a design you can do to make the polymers as a self healable polymers, okay. So this is this idea is really I mean fantastic, and nowadays different type of smart self healable polymers are being developed. This is another one of the very successful strategy by incorporating the ring opening metathesis polymerizable group and charged with the ROMP catalyst, because ROMP catalyst, you know, that is these metal-carbene catalysts are very efficient, okay, and does not really undergo any deactivation very easily. So this is very kind of a fruitful, okay. So this is one of the very recent development using the ROMP, okay. Another, as I told, that development in this domain is the aqueous phase ring opening metathesis polymerization. This is again is very important, because if I can do the polymerization in just the aqueous phase, avoiding the expensive solvents like tetrahydrofuran, chloroform, or other toluene, hexanes, okay, then the whole process will be cheaper, okay. So like here, so what you have to do, I have to make my catalyst water soluble, and how I can do I have to make the neutral complex to a ionic complex, okay, you know, then only the if the, so like a salt, then only it should be soluble in aqueous phase, and it will be under it can be used for aqueous phase polymerization, okay. Obviously your monomer, if it is soluble in aqueous, then the process will be more viable and easy, okay. One of the basic design, you will see how beautiful it is designed. So here you will see that the quaternary amine have been used, so that it actually helps to solubilize. So the Graf's catalyst have been the Graf's first generation catalyst have been modified, okay, to make the water soluble catalyst. So many this kind of catalyst have been developed, like you will see this one, okay. This again the quaternary ammonium centers, which actually helps to solubilize in water, okay. And this is one of the very recent development and achievement by this ring opening metathesis. This is one of the strategy to how you will modify your complex, modify your ligand, okay, and then you can make it water soluble. So like this one, you will see that this phosphine you can functionalize by these chloroamines, and then you make this one, okay, and then ultimately you will get the, after the methylation, the last part, you will get that this amino functionalized phosphine ligands, okay. So after that, so this part, the BHT is basically to make it stable during the whole functionalized process, because because it has a lone pair, okay. It is like a protecting group. So if you don't charge with BHT, there may be side reaction. So it is better to protect with BH3, okay, to kill the basicity of this phosphine, and then you make the protected version, and then you quaternarize, and then this ligand, the protected version of this phosphine ligands, now you charge with the precursor of the Graf's first generation catalyst, and then you get the catalyst which is water soluble in nature due to this ionic complex. Okay. So this you will see that how just a fine designing of the catalyst can make it water soluble, and this one then can be used for the ROMP polymerization in aqueous phase. Okay. So far what we have discussed, I had just give a principle how you can make the catalyst or convert the ROMP catalyst from organic phase to the aqueous phase. Okay. So now I am sure that you have realized that how metal-carbenes have a versatile reactions and applications. In the beginning of the metal-carbene, I told that this is like a single lock or single key of different locks. Okay, you will see that how this one single catalyst or modified catalyst can be used for different purposes. Okay. So in just the next 2 minutes, what I want to do, I just want to give a overall summary of what we have learned in the whole journey of this course. Okay. So the whole concept, okay, of this course is basically to discuss the polymerization of this type of monomers, that is the alkene monomers, to make the polyolefin. Okay. You will see that different type of catalysts we have discussed, and why to develop the different catalysts, because you know that we already there is a lot of catalyst or a lot of initiators for radical anionic, okay, and then why suddenly we needed to develop the organometallic catalyst. The reason we discussed in beginning of our class that the application and property are very much interrelated. Okay, and you know that property again is very much related to the chemical structure, and the chemical structure again is very much connected to the synthetic protocol. Okay. So what actually we are getting from a radical or anionic that may not be the same with the organometallic catalyst, and actually it is true. We have realized, we have now learned that how the organometallic catalysts give a different type of polymers, although the chemical structure is same, but the properties are different. Okay. So those we have learned successfully in this course, and I hope you have enjoyed it. So very specifically I can tell that we have discussed more the catalyst design, what is the chemical structure of the catalyst, what are the metals ion presence there, what are the ancillary ligands are there, what is the basic relation between the structure and symmetry, and the properties of the synthesized polymer. The properties means here the chemical structure of the resultant polymers. Okay, and more specifically the stereoselectivity and tacticity of the polymers. Okay. So you now that most of the catalyst in the organometallic catalyst can very nicely tune the properties, the tacticity of the polymers. As example, if you use a prochiral monomer, as example like propylene or styrene, those are the prochiral molecules, and you can see that how tacticity you can control by using different type of catalysts. Okay. So this one we have discussed extensively. Okay. As example, you will see that here different type of catalyst we have discussed. Obviously the Ziegler-Natta catalyst is discussed to have a basic idea that why it is, although it is very successful, but why exactly it is a lacking, and what is the necessary to develop different type of organometallic catalysts. So here you will see this is the new brand of organometallic catalyst as a homogeneous mostly. Those are actually dominated by the group 4 metal catalysts like titanium or zirconium, and we have discussed extensively that what is the basic and unique properties of bent metallocenes, okay? The chemical, the bonding, the electronic properties, and you will see that how this kind of metallocene compounds are successful in polyolefin synthesis, okay? And most importantly, the controlling the tacticity and stereoselectivity, okay? As example, you will see if you have a C2V, okay, then the C2V point group, we got the atactic polypropylene, okay. If we have a C2, then we got the isotactic, okay. If we have the meso CS, then we got atactic. If CS, then syngiotactic, okay. And if you have a C1, then it's actually variable, but mostly isotactic, okay. So if I can choose my catalyst, okay, according to the symmetry, the metallocene catalyst according to the symmetry as per my requirement. If I need a atactic, I'll choose a catalyst with C2V symmetry. If I need isotactic, I'll choose the category with C2 symmetry. If I need to have a syngiotactic polymer, I will choose the metallocene with CS symmetry, okay. So in conclusion, today we have discussed the industrially important polymers through ROMP, the unique properties of the polymer, and importance, why those polymers are so important, like PDCPD, polynorbornene, still those are used heavily, and the how ROMP, okay, provides to design smart polymers, smart healable polymers, and very interesting, and that is actually the future scope of this kind of catalyst is the ROMP in aqueous phase. So industry will like it to make the polymers aqueous phase, because it will be more industry viable, more economic, more easy to handle, okay. So for this course, these are the most important reference books, like Organometallic Chemistry of Crabtree by John Hartwig, by Astruc, by Gupta and Elias, and with this one I am very much hopeful that you all have enjoyed this course, okay, and you have now understood that what is the journey. It is a long journey. It is not like a 3 years, 4 years research. It is a long journey how to have a efficient organometallic catalyst for the olefin polymerations, and how the industry has been accepted for different type of organometallic catalysts over the time. So with this, thank you very much, and best wishes for your exam. Okay, thank you.